MIMO, multiple input, multiple output technology using multiple antennas at both the transmitter and receiver sides is widely proposed as the key technique to enhance the link quality and/or improve the spectrum efficiency. However, increasing the performance of mobile terminal devices implies the use of more sophisticated signal processing algorithms. This gives tremendous challenges for real-time hardware implementations at baseband. GEDOMIS, generic hardware demonstrator for MIMO systems, is a multi-antenna wireless communication testbed that enables the prototyping and evaluation of physical layer algorithms targeting MIMO systems. This is feasible thanks to its heterogeneous and reconfigurable structure comprising mixed FPGA and DSP baseband signal processing components, which can be used for the implementation and real-time validation of broadband wireless communication systems. GEDOMIS also comprises a radio frequency front-end that allows the development of multi-standard receivers. A key instrument of the testbed is the multi-channel emulator that facilitates the verification and testing of MIMO designs prior to field tests using realistic mobility scenarios. GEDOMIS is currently hosting a mobile WiMAX system featuring a 2x2 MIMO configuration and a high channel bandwidth of 20 MHz. The physical layer signal processing algorithms were deployed using a real-time custom FPGA implementation. The specifications of this high-capacity wireless system are an indicative proof of the versatility and processing power of GEDOMIS. GEDOMIS is one of the very few existing real-time MIMO testbeds that hosts a custom physical layer implementation of a broadband wireless access standard. The compliance of our 2x2 MIMO testbed with the IEEE 802.16e standard was verified using WiMAX certified software packages that enable physical layer measurements. The testbeds operating in offline mode cannot be used to explore MAC protocols and receive long data frames due to timing and memory constraints respectively. Besides, it is worth mentioning that closed-loop MIMO schemes cannot be realized in such testbeds. GEDOMIS comprises the technology, equipment and specifications that allow the design, implementation and real-time validation of top performance systems featuring different MIMO schemes. The FPGA-based deployment of the mobile WiMAX receiver required thousands of lines of custom VHDL code. The challenging RTL implementation involved advanced pipelining techniques and imposed numerous optimization stages in order to minimize the processing complexity, implement intelligent memory utilization techniques, address the stringent timing requirements, and remove radio frequency signal impairments. The 20 MHz channel bandwidth of the mobile WiMAX system hosted in GEDOMIS exceeds the WiMAX Forum radio conformance test profiles of the IEEE 802.16e standard. This fact positions GEDOMIS in the forefront of real-time MIMO testbeds used for applied research purposes. A fully integrated and reconfigurable phase-coherent multi-channel Wi-Fi RF receiver designed at the CTTC was upgraded to match the WiMAX testing scenario. Both the Wi-Fi operation at 2.4 GHz and the WiMAX one at 2.6 GHz demonstrate an adequate performance in a 2x2 MIMO configuration. GEDOMIS is equipped with instrumentation able to generate both custom and standard compliant signals, emulate the radio channel conditions, and analyze troubleshoot the received signal at any frequency band up to 6 GHz depending on the test scenario. The transmitter was rapidly deployed in MATLAB and validated using WiMAX certified signal generators and software libraries. The first processing block of the transmitter is a randomizer that pseudo-randomly scrambles input data. The modulator maps data into constellation points and the subcarrier mapper modulates the allocated subcarriers. A preamble generator generates a symbol to precede the burst depending on the transmission type. The pilot subcarrier mapper inserts pilot subcarriers into each data burst. The inverse FFT transforms the frequency domain signal into a time domain signal, and a cyclic prefix, CP, is inserted to obtain the complete OFDM signal. The I and Q outputs of this MATLAB model are written in 2 data files and then uploaded to 2 Agilent vector signal generators appropriately configured for a MIMO signal transmission. The signal generators play back in real time the I and Q waveforms, upconvert the signal, and provide the desirable RF output. The Electrobit PropSim C8 channel emulator allows accurate multi-channel emulation of custom or standardized models at the laboratory. This is feasible by adding complex and time-varying effects of multipath and Doppler shifts in the digital domain by adjusting the tap amplitude, delay spread, operation frequency, and mobile speed. For our 2x2 MIMO scenario, 4 uncorrelated multipath fading channels were assigned in the ITU Vehicular A and the ITU Pedestrian B channel models. The channel emulator was tuned to provide optimal performance in terms of noise floor, dynamic range, and EVM, allowing sufficient safety margin for its operation. The receiver comprises a high-end radio frequency front-end, 2 noise signal generators, a data acquisition board from Lurtec with 8 AD channels, and a baseband signal processing platform from Lurtec carrying 4 Xilinx Vertex 4 FPGA devices and 4 Texas Instruments DSP microprocessors. The baseband part of the receiver is a custom VHDL implementation fitted in 2 FPGA devices. The input of the receiver comprises the automatic gain control component, AGC, which adjusts the dynamic range of the input signal to fit the operating range of the AD converters, preventing their saturation. The digital down converter, DDC, extracts the in-phase and quadrature component of the signal. The synchronization block detects the beginning of the data period and thus the position of the OFDM symbols to apply the FFT. It is also estimating any residual carrier frequency offset, CFO, that is used to finely tune on the fly the numerically controlled oscillator, NCO, of the DDC. The OFDM demodulation includes the CP removal, the FFT, and the removal of the guard band and the DC carriers. The subsequent blocks are related with the organization, randomization, and grouping of the carriers according to the mobile WiMAX frame definition and the pilot's extraction, which are scattered along the signal bandwidth. When a MIMO configuration is used, each processing chain at the receiver has to estimate the corresponding channels from all transmit antennas. The channel frequency response at the data subcarriers is extracted by applying a second-order polynomial interpolation to the estimated value at the pilot's positions. Finally, the decoding of Alamuti's code matrix A is applied on a per subcarrier basis in 2 transmit antenna systems.